Bismillahirrahmanirrahim. In this video, we are going to discuss the operation of the quasi-square waveform inverter. The circuit diagram for the full bridge inverter is shown in front of you. Now we see how we can generate the gate pulses for the quasi-square waveform. For that, I am going to consider a triangular waveform like this. Let's assume that the magnitude of this triangular waveform is AC, and this waveform is called the carrier waveform or carrier signal. We compare this carrier signal with a rectangular waveform. So this rectangular waveform is shown over here. Let's suppose that the magnitude of this rectangular waveform is AR. This is called the reference waveform or the reference signal. So we define a term modulation index which is the ratio of these two waveforms magnitude. AR by AC, the magnitude of the reference divided by the magnitude of the carrier, gives us the modulation index. We generate gate pulses by the comparison of these two waveforms. So if I sketch a line from their point of intersection, so it will look like this. Now we define a logic, and what is that logic? That when our reference waveform is higher than the carrier waveform, we have logic high at the output. So if we compare the two waveforms, over here we will be getting logic high because our reference is higher than the carrier waveform. So we will get this gate signal, and this is applied to switch S1 and S4. When this gate signal is applied, the inverter output voltage will be equal to plus Vs. So this is the gate signal applied at switch 1. So I am going to call it VG1 or VG4. Both of them are same. So when we apply this gate signal to those two switches, what will be our output voltage? Our output voltage will be equal to plus Vs. So basically our full bridge circuit is going to act as a class D amplifier. When we apply the input gate signal to switch S1 and S4, exactly same wave shape appears at the output but is amplified to the voltage level Vs. The gate signal is usually in the range of 5 to 15 volt. But your output voltage depends upon the DC source that you have connected. So when you apply the gate signal, you will get the output, otherwise there is no output. And this waveform, this gate signal is centered at pi by 2. Similarly, your output voltage that is appearing across the load is centered at pi by 2. Now from the negative half cycle of the rectangular waveform, we can generate the second pulse, and that second pulse is sketched over here. This gate pulse is applied to our switch S3 and S2. At that instant of time, there will be no gate voltage for the switch S1 and S4. They will be in the off state. So once we turn on S3 and S2, the load voltage will be opposite and will be equal to Vs in terms of magnitude. So our load voltage will be at minus Vs level, and this will be the voltage waveform. Then in the positive cycle of the rectangular waveform, we generate the pulse again, and that is applied to the switch S1 and S4, and the output voltage of the inverter is plus Vs. If you look at this part, this is centered at 3 pi by 2. This is pi and this one is 2 pi. So I have sketched one complete cycle at the output. The negative cycle, the negative half cycle, and the positive half cycle. Positive half cycle is centered at pi by 2 and the negative half cycle is centered at 3 pi by 2. So if we look at this waveform, this is the output voltage waveform. I am going to mark it V0. It's a quasi square waveform. So we have a certain dead band and on time in each half cycle. The on time is this one and the dead band is this one. Dead band is equally divided on the start and at the end of the pulse. As we are generating this with the help of the rectangular waveform, so if we increase the magnitude of the rectangular waveform like that, so the width of this gate pulse will increase equally from the both sides. So our this gate pulse will remain centered at pi by 2. Similarly over here, when we are increasing the magnitude of the rectangular waveform, the width of the second pulse will also be increasing. So our output voltage waveform will be exactly the amplified version of the gate pulses, but in the positive half cycle positive voltage and in the negative half cycle the negative voltage. It will remain centered at pi by 2. This is the center point. Similarly, the negative portion will remain centered at 3 pi by 2. So when you change the magnitude of the reference voltage, your pulse width will increase or decrease. Let's consider another case. Let's suppose I am going to decrease the reference voltage waveform to this level, so our pulse width will be reduced. So this will be the new pulse that will be generated by the comparison of the reference waveform with the carrier waveform. The carrier waveform is the triangular waveform. So our pulse is centered at pi by 2 and 3 pi by 2 and its width is changing. So we call it the pulse width modulation. The width of the pulse will be changing as we will be changing the reference, and the area covered will be changed. Okay, so as the area covered will be changed, so RMS output voltage will get changed because that is the function of the area under the curve. So now let's suppose that in the output voltage waveform, the width of the pulse is del in the positive half cycle. The equal width will be there in the negative half cycle because we are generating the pulse by comparison of the triangular waveform and the rectangular waveform, which are equal in magnitude in the positive and the negative half cycle. Okay, so this waveform now can be used to extract parameters of the inverter output. The first thing that how we can calculate the RMS voltage at the output. So as we know that our pulse is centered at pi by 2, so this angle will be del by 2 and this angle will be del by 2, right? So this angle will be equal to pi by 2 minus del by 2 and this angle will be pi by 2 plus del by 2. Similarly, if I talk about the negative part, this angle will be 3 pi by 2 plus del by 2 because this is del by 2. This pulse is centered at 3 pi by 2 and the width is del. so it will be del by 2 on both sides. So this angle will be 3 pi by 2 minus del by 2, right? So now to calculate the RMS output voltage, we can write down an expression that V naught is equal to 1 by 2 pi integration from pi minus del by 2 to pi plus del by 2. This is pi plus del by 2, this is pi minus, the starting edge is pi minus del by 2. And during this interval, the magnitude of the output is Vs, so the square of that one, because we are calculating the RMS value, and the integration with respect to d omega t, because we have considered the limit in terms of angle. So this covers the positive part. Now as we are calculating the RMS value, so for the negative part I am just going to multiply it with 2 and then taking the under root. So now if we simplify this expression, we are going to get Vs into del by pi. So our pulse width controls the RMS output voltage. So RMS output of this quasi square waveform inverter is Vs into del by pi, right? So we have calculated the RMS output voltage considering this pulse, this output, and we have defined the limit for this waveform. Okay, now let's look at the Fourier analysis of this output voltage waveform. We have already seen the expression, Fourier expression of a quasi square waveform. So applying it directly, this output voltage now can be written in terms of Fourier expression like this: 4 Vs by n pi into sine n del by 2. Del by 2 is the half pulse width. If your pulses are centered at pi by 2 and 3 pi by 2, then you can use it directly. So n varies as an odd number up to infinity. Odd harmonics are present in this waveform, and the phase part is sine n omega t. So your output voltage is expressed like this, right? So this del by 2 is basically the half of your total pulse width, half of pulse width, del by 2. We can also represent the Fourier series in terms of the dead band. And what is the dead band? Dead band is basically this part, this one and this one, dead band in the positive half cycle, and equal dead band we have in the negative half cycle, equally distributed on the two sides of the pulse, right? So let's suppose that this dead band, this is gamma by 2, and equal dead band will be over here, gamma by 2, and similarly over in the negative part, this is del by 2 and this is del by 2. So we can use this dead band to evaluate the Fourier series. So for all odd harmonics up to infinity, 4 Vs by n pi, instead of sine, if we are going to use the dead band, it will be written as cos n gamma by 2 into sine of n omega t. So we can write the Fourier series in terms of the pulse width or the dead band. So this is the half of dead band, this part. So you can use either the pulse width or the dead band information of the pulse, and you can represent your signal in terms of Fourier series. Okay, now looking at this expression, you can see that we can cancel a certain set of harmonics. Let's write down that one again. V naught is equal to this expression, sine n del by 2 into sine of n omega t. Okay, so in this, we know that only odd harmonic exists, but if we consider n is equal to 3, so you will see that sine of 3 del by 2 will be equal to 0. So from here, if I calculate the del, that is the width of the pulse, so that should be equal to, in terms of angle, 2 pi by 3. So if our pulse width is equal to 2 pi by 3 in this waveform, then our third harmonic will be cancelled out. So if I draw this Quasi square waveform again, such that it is positive part is centered at pi by 2 and this del is equal to 2 pi by 3 in terms of angle, so this point will be pi by 6, and this point will be 5 pi by 6, and we have pi over here. And similarly, the negative part that is centered at 3 pi by 2, if the width of the pulse is 2 pi by 3 and we have the equal dead band on both sides, so for this our third harmonic will be absent, right? So del over here is 2 pi by 3, so del by 2 will be equal to pi by 3. So now if we use this pulse width in this expression, so V naught will be equal to 4 Vs by n pi, where n is in odd number up to infinity, sine of n pi by 3 into sine of n omega t, that is the Fourier series representation with this pulse width. And in this, if I place n is equal to 3, sine of 3 pi by 3, that will be equal to 0. Similarly, if I place n is equal to 9, so sine of 9 pi by 3, that will also be equal to 0. So all the triplets are absent, so no triplet harmonic is present. So triplets are absent in the Quasi square waveform if del is equal to 2 pi by 3, that is the pulse width in each half cycle, or if I say the dead band is gamma, so that is equal to pi by 3, 60-degree dead band, equally distributed on both sides. So if gamma is equal to 2 pi by 3 or del is equal to 2 pi by 3 or gamma is equal to pi by 3, your triplet harmonics will be absent. So if I quickly sketch the spectrum of this Quasi square waveform, so if I say the fundamental component is, let's suppose V1 fundamental component, the second harmonic will be absent, the third harmonic will be absent, fourth harmonic will be absent, fifth harmonic will be there, and the magnitude of the fifth harmonic will be V1 by 5. So here I am plotting the Vn, the absolute value of that one. So sixth harmonic will be absent, seventh harmonic will exist, that will be having the magnitude V1 by 7, then eighth harmonic will be absent, ninth will be absent because it is the multiple of 3, 10th will be absent because it's an even, and 11th harmonic will be there, so V1 by 11. So this is the magnitude of the this is the spectrum of this Quasi square waveform. Now if I say that cancel the fifth harmonic and its multiple from the inverter output waveform, so what you are going to do? You are going to look at the output voltage waveform Fourier expression. So in this, if sine of n del by 2 is put equal to 0, where n is equal to 5, so sine 5 del by 2 equal to 0. So from here, if you calculate the del, that will be equal to 72 degree. So if the pulse width will be equal to 72 degree, right? So fifth harmonic and its multiples will be cancelled out. So by changing the width of the pulse, you can cancel one particular set of harmonic from the output voltage waveform. For the pulse width of 120 degree, we have cancelled the third harmonic. For the pulse width of 72 degree, we will be cancelling the fifth harmonic and its multiple. So what we can conclude from here, from this discussion, we can cancel one set of harmonics. And what I mean by a set of harmonics means if I say the third harmonic, then all of its multiples. If fifth harmonic, then all of its multiples. If seventh harmonic, then all of its multiples, but one set at a time. If you are cancelling the third harmonic, fifth harmonic will be present. If you are cancelling fifth harmonic, third harmonic will be present. So with the help of the quasi square waveform, you can cancel one set of harmonic by controlling the pulse width and the dead band in the inverter output voltage waveform. Okay, now how to cancel two or more harmonics? You will have to increase the number of pulses per half cycle. You have one pulse in one half cycle, either in the positive or the negative half cycle, so you can cancel only one set of harmonic. If you want to cancel two harmonics, you require two pulses per half cycle, or at least two edges to be controlled in one half cycle. So by increasing the number of pulses per half cycle, we can control the spectrum. We can shift the harmonics to the higher order, or we can cancel lower order harmonics. So that gives the starting of the PWM inverters, that if we increase the number of pulses, we can cancel set of harmonics. Okay, before ending this lecture, what will be the frequency of the output voltage waveform? The frequency of the output voltage waveform will be that of your reference waveform. So if you change the frequency of the reference waveform, your output frequency will get changed, right? And how to change the output voltage? For output voltage variation, you will have to change the modulation index. So if you increase the magnitude of the reference voltage waveform, more area will be covered because pulse width will be increasing, so RMS output voltage will be increasing. If you decrease the magnitude of the reference waveform, that means you are decreasing the modulation index, your output voltage waveform will be, your output RMS value will be reduced, right? Thank you very much.